members of our group are Joe, Fergus, Charles and Cam. We've been working together throughout the semester on a Robotics Studio 2 project where we control a UR3 to play chess. But currently, we generate the chess moves for the robot to play using Stockfish, an incredibly powerful chess engine. However, for this AI project, we are going to replace Stockfish with our own AI algorithm to generate chess moves and outsmart human opponents. Our engine will need to be able to generate the best move from any given position. The benefit of training an AI model for chess is the abundance of data available. There are terabytes of recorded chess games and a large selection of high-quality games that can be downloaded for free. The standard form for this data is a PGN file, which contains metadata tags and the moves that were made. From this data, we can extract each position of the game and analyze the impact of each move.
Up until now, we have tried several methods to make the AI work reliably. The first technique we try is using support vector machines with GPU accelerations using CUDA cores. We have tried 3 different iterations of SVM. As you can see on the right-hand side chart, it had acceptable win and draw rates against a random player who only make random moves without any strategies, indicating that the SVM model is able to make sensible gameplay. However, its strategies were still incomparable to Stockfish, which had a 100% win rate against our model. Therefore, we have to do more research to find a more optimal and complicated approach for our chess playing applications. After that, we tried using a DeepQ network, which is a reinforcement learning method, with our own reward functions. And this approach also faced significant performance challenges. After 5 different iterations, with a decent amount of adjustment in the training code, all iterations still have a near 100% loss rate against Stockfish. This experiment prompted us to rethink the viability of DQN for a chess engine, as the poor results are unacceptable. Surprisingly, at the end, what ended up actually working is using a convolutional neural networks, a CNN, with supervised learning. As you can see in the videos below, we are playing chess against our newest AI model trained by this supervised learning method. This helped the net to learn the spatial relationships which are critical for chess. The network was trained using 3.9 million chess positions as input and the move made by master players as a target output. The current board position is input to the neural network as a 13 by 8 by 8 matrix where each individual channel contains the data of where all of the 1 of the 12 types of pieces are located on the board, and the 13th channel encodes all the legal positions in the current positions. The neural network output a matrix of 2 by 8 by 8 where the first channel is where the piece will be moved from and the second channel is where the piece will be moved to. Additionally, the neural network implements attention layers. This was implemented because the model was only seeing local threads, likely because of how the kernels in the convolutional layers were working on a more local level. The attention layers were targeted toward finding the relationships between each and every squares. This was inspired by large language model, which create an attention matrix where a matrix is constructed with each input words in the rows and each input words in the columns. The values represent the connections between the words. This attention layers in the net help with long-range visibilities and understanding of how certain pieces have impacted across the board. We speculate that the final model is expected to have an elo of approximately 1,500. As you can see in the image, it has a win rate quite similar to a Stockfish at elo 1,350. Sometimes it's even higher. We have uploaded our model to Lichess for other players and even our classmates to combat the model, and the end results are pretty satisfying, with overall 16 wins, 4 losses and 1 draw. We will provide you a link for you to test this model yourself as well. Thank you very much for tuning in.